I would like to introduce the fourth lecturer of our school. So we have Oliver Schlotterer, who is an associate professor at the University of Uppsala. And today he will be talking to us in his area of expertise, with great expertise, namely string amplitudes. Thank you very much and welcome, Oliver.
Yeah, thanks a lot for the kind introduction, and I'm very grateful to Jorgos and Volker for hosting this school, for investing into the next generation. Yeah, it's a pleasure to lecture in front of such an energetic gang of young people. I hope we are still energetic at this late time. Let me try my very best to contribute to the energy level and give you a gentle start into the topic of string amplitudes. So let me try to convey some enthusiasm about this subject. Okay, I'm normally supposed to start off with a motivation right away, but I chose to delay this for maybe half a lecture and to first draw some pictures to give you a rough idea of what we will be discussing. And after giving the rough picture, it's probably easier to state some motivation points in favor of string amplitudes. Okay, so I was told that I should be gentle in what I assume about string theory. So let me just give a very, very rough picture of how to think about string theory for the purpose of this lecture. Maybe you heard more about the bosonic string, so don't worry too much about this super here. You will see the difference between bosonic string and superstring in action very soon. But let's say for now, let's think of superstrings as being field theory plus extra, plus in fact an infinity of extra states, which are the heavy vibration modes. And I think just 5 minutes ago we had the formula for the respective mass squares here on the slides of Gleb. Both for bosonic strings and for superstrings, there are plenty of extra vibration modes whose mass squares scale like an integer n times some fundamental mass parameter. Let's call it m string. Well, I don't want to be too specific what that string scale is. Actually, we don't know. But what we can say for sure is that since we haven't seen any string signatures at colliders, this m string is for sure beyond the reach of colliders. And since this m string is very bulky to write down, I'll refer to it in a slightly different combination. Instead of m string, you will see alpha prime, the Regge slope or the inverse string tension, and it's just related to m string through this simple relation 1 over m string squared. So alpha prime has units of length square. This is something you will see all over this lecture. Okay, I told you about the masses occurring in a string spectrum. Also, there are higher spin states. Also, this you have just seen on Gleb's slides. And here, in case of the superstring, once you fix the mass level, little n, then the spins go all the way to n plus 1 at level n. This is something that you will shortly read off from an amplitude. Okay, what about that field theory? So one virtue of the superstring is that you don't have to worry about the tachyon. There's no need to go for a negative mass level. So the smallest m squared you'll ever see is the massless level, where in case of the open superstring, you will find 10-dimensional superyannuals. This is, if you wish, the mother of all maximally supersymmetric gauge theories. You can dimensionally reduce this to n equal 4. Okay, maybe not to the mysterious 2,0 theory in 6 dimensions, but yeah, you can dimensionally reduce it to a lot of things. And if you look at the massless spectrum of the closed superstring, here you get supergravity, and there are actually 2 choices in the critical dimension 10 of the superstring. There are 2 ways to design a supergravity multiplet with 32 supercharges, and these 2 choices got the funny name type A and type 2B. This is about how you adjust the relative chiralities of the supercharges. Yeah, this is supergravity. Okay, so I will say the word field theory many, many times, and I usually refer to either 10-dimensional super Young-Mills, if it comes in an open string context, or I'll refer to type 2A, type 2B supergravity when it comes to a closed string context. This is what will be meant by field theory. But okay, we will scatter strings, so let me give you a schematic idea of how string amplitudes can be organized. And I'll start by just stating the topological expansion, the stringy version of the loop orders in field theory. And that is something which is, of course, common for both superstrings and bosonic strings. Okay, let me pick you up from the same kind of intuition as if we were to scatter point particles. Suppose you want to scatter open strings. Then you would draw almost the same kind of cartoon as you would do for point particles. There is some stuff coming from far, far away, and that will eventually meet. Two open strings colliding, and well, after the collision, something will go out. It can be one state, two states, maybe even more, but let me just draw the cartoon for a 4-point scattering process. And let's follow the same kind of mantra as you know from field theory. Let's sum over all possibilities how this process can happen. Yeah, so this is something like a generalization of a world line. A point particle smears out a world line, whereas a string, which is a collection of point particles, will smear out a two-dimensional surface, a so-called world sheet, as the string propagates in space-time. So I should draw all possible world sheets that are compatible with the external state configuration. So there's, for instance, the possibility to redraw the picture with a hole somewhere in the middle of the world sheet. It's still compatible with that scattering process. And of course, nobody would stop me from adding more and more holes to it. So here, the perturbative expansion of an open string, 4-pi amplitude, is just sum over any number 0, 1, 2, ... of holes. Okay, I already said it several times. This is following in close analogy to the analogous perturbative expansions of field theory amplitudes. So if you were to repeat this kind of grading in field theory, you would draw a couple of tree-level diagrams first. So no matter whether you look at Young-Mills or supergravity, there will be combinations of cubic vertices and quartic vertices in the Feynman rules that you can, for instance, read off from a Lagrangian. And then the next bunch of Feynman diagrams will be at the one-loop order. Box and triangle and bubbles, as we saw it in David's lecture. And here you can go higher in loop order if you wish. But one important statement already here is there's always a backwards compatibility. You can go from strings to field theory, well, by just shrinking the strings to point particles. So let's reduce the string length. And there was a length parameter. It's alpha prime, where the alpha prime to 0 limit leads you from string world sheets down to Feynman diagrams. And this statement actually applies loop order by loop order. So you don't need to worry about a tentative mixing of tree and loop diagrams as long as you start from a given world sheet genus. Okay, so the first remark to be already made right here is one nice feature of string amplitudes is that in the alpha prime to 0 limit, you get many Feynman diagrams from a single world sheet. Maybe the wow effect is not so visible here in the 4-point case, where I'm telling you about 3 Feynman diagrams from one world sheet. But as you know, as you increase the number of legs, the combinatorics some sort of explodes. There's a double factorial growth of the tree-level Feynman diagrams with the number of external legs, but it's still one single world sheet, which reproduces all of these Feynman diagrams at once. Okay, maybe we need a caveat at the one loop order. There's not only the topology here, but also the Möbius strip that I didn't draw. But for sure, it's many final diagrams from very few worldsheets. So 3 levels, a single one. By the way, is the handwriting okay in terms of size, shape, and so on? Yeah, just interrupt me if not. Good, so this is the story for open strings, but let me also draw the corresponding cartoon for closed strings. Let's start with the same kind of intuition. Let's have the closed strings come in from past infinity, meet and go out. So this time it's not an infinitely long strip, but an infinitely long tube. So just imagine this is the closed string and it propagates through space-time going to the right. Okay, and once more I can repeat the game with the topological expansion. I can redraw this process, but now with a hole. So now it's something with the topology of a torus, and again you can go on and go on and go on. Okay, and amusingly, the story with the Feynman diagrams goes through literally as in the open string context. So here the alpha prime to 0 limit is very forgetful, at least as far as the reproduction of Feynman diagrams is concerned. You get the very same Feynman diagrams here from the alpha prime to 0 limit of the closed string worldsheet, as long as you match the number of holes for open and closed strings. And again here, alpha prime to 0 limit of this torus diagram gives you back the box integral and possibly others depending on the amount of space-time using. Okay, as you will see in the course of this lecture, the closed string degrees of freedom are in a certain sense doubled relative to the open string degrees of freedom. So at the level of the spectrum, there's something like double copy going on. And I'll also show you some simple incarnations of this double copy at the level of full string amplitudes, like the KRT formula at tree level. So a schematic statement to be made right here is that there is a connection between open and closed strings, double copy, valid at any range of alpha prime. But of course, if double copy is generic with respect to alpha prime, it must survive in the alpha prime to 0 limit. So the respective field theories that you get at alpha prime to 0 must also be related by double copy. This is something which you may not necessarily expect by looking at a Yang-Mills Lagrangian or a supergravity Lagrangian, but by their string theory origin, the amplitudes of perturbative gauge theory, perturbative gravity, must also be related by some sort of double copy, which you can think of as a shadow of this stringy double copy that I'll spell out in later lectures. Okay, now these cartoons here with the long strips and tubes are useful to give some intuition. But when it comes to doing the math, maybe it's beneficial to trade these infinitely long legs and tubes for something more handy. And here we can make use of the conformal symmetry on the worldsheet to map, for instance, this guy to something simpler. I used the buzzword topology a couple of times. So this diagram is topologically equivalent to a punctured disk. And the main idea is that we can use conformal symmetry to trade the infinitely long strips and legs for just a point-like defect. Here, this bullet means to say, put a little hole on the boundary of the disk. So given that there are 4 external states, 4 infinitely long strips, there will be 4 punctures on the boundary of the disk. Yeah, so the buzzword boundary is also important. That's something only for the open string, that here, this is really an honest worldsheet boundary, whereas in the closed string case, this one is topologically a sphere, which does not have a boundary. So here, with the analogous mapping, external states go into punctures. This 4-point closed string tree amplitude is governed by a 4-punctured Riemann field. Okay, and the same games, of course, go through at loop level. So there, the specific open string diagram at one loop that I've drawn for you is topologically an annulus or a cylinder. So you can replace this one by that cartoon. So here, there are two worldsheet boundaries, an inner one and an outer one. In this drawing, all the external states are sitting on the same boundary, which you may call a planar cylinder. But of course, I could also put an infinitely long strip on the inner boundary. So just as a side remark, there also exists the corresponding non-planar configuration. Now, I'm not brave enough to draw it in this way, but at the level of punctured cylinders, the non-planar case is something like that. And there's also a Möbius strip diagram, which I won't even attempt to draw. But okay, this is probably beyond the scope of this lecture. Good, let's repeat that for the closed string. Here, I already said it. This one-loop diagram for closed strings has the topology of the torus. So here in the 4-graviton case, this is about a 4-punctured torus. Good, so as I already explained, one can map external states to punctures. Point-like defects. Here, these bullet, as the later command would be. And now what's the actual calculation you need to do to evaluate a string amplitude? So again, it's the mantra of integrating over all possible histories. And here, the picture of the punctures. All possible history means integrate over all conformally inequivalent ways to put punctures on these given surfaces. Okay, this was a mouthful of information. So we need, when it comes to computing amplitudes, we need to integrate. And let me now give you the mathematical buzzword for that. We need to integrate over the modular space. M, G, semicolon N, of N punctured genus G surfaces. So this is how you can explain to a mathematician what you are doing if you compute string amplitudes. Okay, yeah, so let me add one more remark to the story with boundary. So for open strings, the string itself has two endpoints, and these endpoints will later on be docked on the boundary of a worldsheet. And this is where color comes into the game, or more generally, non-abelian gauge freedoms. So I guess you have seen in the lecture of Johannes Henn the notion of color decomposition, which is super useful to organize gauge theory amplitudes into digestible packages. And this kind of color decomposition comes, if you wish, by definition from the string worldsheets. Color decomposition. This comes from the fact that you have open string punctures on a boundary. So let me elaborate. No matter whether we are looking at a disk or a cylinder or something of even higher genus, whenever some part of the worldsheet exposes one boundary, then you have to be really careful in which order you attach the open string states. Or more precisely, you have to worry about the cyclic equivalence clause. So at the level of an open string amplitude, the story goes as follows. To the open string endpoints, you can associate some extra degrees of freedom, so-called chain pattern factors, that introduce the notion of color or non-abelian gauge symmetry. And once you have committed to a cyclic ordering on a given boundary, this diagram will automatically contribute the following trace to your amplitude. So here I'm already looking at a boundary with n punctures on it. Yeah, so I will loosely refer to that as color, and in the string theory textbooks you will find it under the name chain pattern factors. Okay, and the notation is such that, so for each master's external open string state, I will call it Gluon, and so it will be valued in the adjoint representation of some gauge to un, and accordingly I need to label the external state with the adjoint index. Okay, so this is how the color dependence comes about from the viewpoint of string perturbation theory, and we will content ourselves to computing color stripped amplitudes for open strings. And of course, for the closed string, the worldsheet has no boundary, and these color degrees of freedom don't arise. Okay, so this concludes the super rough picture of string perturbation theory that I wanted to give. And let me now give you a semi-concrete example of how the disk calculation proceeds. So let's zoom onto one of these many worldsheets on the blackboard and take as a hopefully inviting example the 4-point open string tree-level amplitude. And here, the cyclic arrangements of the labels here, this already tells you which trace sector I'm looking at. So here, the cartoon is the disk. Now, it's already drawn without the long legs. Here it's a disk where the cyclic ordering of the punctures is such that 2 is the neighbor of 1 and 3. Okay. Yeah, I was advertising these punctured surfaces before as being nicer to do calculations as the long legs. But something which is even nicer than the punctured disk drawn in that way is some integral along the real line. So the power of this conformal symmetry, which allowed us to introduce the punctures, is not yet over here. You can do a little bit more, something that I'll explain later, as modding out by SL2R. And what the prescription is, you can always afford, at the disk level, to fix any 3 punctures you like to any points on the real axis that you like. Okay, something I should have said earlier. The idea is to map the disk boundary to the real line. And here I'll show you the example in the choice where Z1 goes to 0, Z3 goes to 1, and Z4 goes to infinity. This choice will basically then exhaust the conformally inequivalent choices to arrange the worldsheet. And of course, I could have fixed instead Z1, Z2, Z3. There's a zillion of options. Also, you can fix the punctures 2, 3, 4, but maybe your calculation wouldn't benefit. Okay, so here on the real line, we have Z1 on the origin. We have Z3 at 1, and then, which is a little bit tricky to draw for me, there is Z4 at infinity. And now, the job is to integrate the leftover punctures in any way which is compatible with a cyclic ordering. Okay, so the leftover puncture is obviously Z3, and the ways that are compatible with a cyclic ordering is, it should better sit between Z1 and Z3. Okay, so the leftover integral to do is this one. So here I'm spelling out how that fancy sounding integration over the moduli space, how this specializes in a color-ordered open string tree-level context.
Excuse me.
Yes.
The thing in your drawing is like the third dimension. So for the open string, I see that the picture is like 2 dimension. Then you draw the circle.
It's strictly speaking not necessary. It's just a desperate attempt to visualize it a little bit that it's really a disk.
So
the problem is
like it's just the surface of that. Okay, so it's a 2-dimensional things.
I was worried that the disk looks exactly like a sphere.
Okay.
And I wasn't sure whether these little lines here make it clear enough that the sphere is different from the disk.
Like a frisbee.
Frisbee, yes, yes. We're integrating over the frisbee boundary.
Thank you.
Thank you. All right, so let me go into more detail about this introductory example here. Let me tell you about this integral that we are left with, and let me give 2 complementary perspectives how you can, with limited effort, extract a lot of stringy physics from playing with that integral in different regimes. Okay, what I won't tell you is what the full expression for the integrand is. So here is the black box part of this example. After some work on the integrand, that's something for later lectures, you will arrive at the following factorization. So here's our target, the 4-point open string tree amplitude, which will be a function of alpha prime. And it turns out you can factor out the entire tree-level amplitude of super-Young-Grams. So there's a lot of CFD machinery involved that you will get an idea of, but I hope you're willing to trust me for the moment. You can shake it to the point that all the polarizations are completely disentangled from a scalar integral. So when we are scattering gauge bosons, there will be some polarization vectors that contract momenta, or maybe other polarization vectors. So all of this is hidden in here. All polarizations. And everything left can only depend on the momenta. Just to repeat, we are doing color strip amplitude, so no color either. Good, and now this set momentum dependence, it comes through an integral of the type I've just sketched for you. And I hope you're willing to trust me that the integrand looks something like this. There is the puncture Z2 raised to the power of a Mandelstam invariant. And before anyone is getting a heart attack about having k dot k in the exponent, the convention probably throughout the lecture is that the Mandelstam invariants are dimensionless. So the obvious part is that Sij will be proportional to this one, but this is of order length to the -2, so that's better put in an alpha prime into the definition to make it dimensionless. Okay, and it's that integral that I want to look at from different angles. And let's refer to that integral as Z4 point. And as I stressed, the nice feature here, that I hope you are buying it right now, is the nice feature is that you only have dependence on the momenta, but no more polarizations. So we don't have to worry about too many things at the same time. Okay, so it's this integral Z4 point that I want to offer 2 perspectives on, where perspective number 1 is the state exchange viewpoint. how can we learn about the string spectrum from this integral here? Okay, I think as a general strategy, when you're looking at an integral, the first thing you check is whether you'll be able to find a primitive. This would be super nice if we could just write down a primitive. Maybe this is too hard in the present form, but maybe you want to series expand the second factor here. Maybe you want to series expand it in such a way that you can find a primitive term by term. So let me offer this representation here, where, whoops, we do a binomial expansion of this 1 minus z2 to the s to 3. So you get a series of this type. Of course, we cross fingers that the integration commutes with the infinite series. And now we're in a good position to take the primitive term by term in the series over n. Okay, so now I made a strategic mistake about not leaving enough space. So, yeah. This calculation goes on here. So, as I was saying, let's take the primitive term by term in the series over n. The primitive, it just amounts to pulling down the exponent. Pulling down the exponent in this way. And, okay, the rest is, well, you get what you get, some binomial coefficient involving the other Mandelstam variable. And, yeah, that's already it. And now to dig out some physics from there, let's just look at the leading terms in the sum over n. So you have a variety of poles at all negative integer value for S12. These poles signal that they are masses in the spectrum, masses of states that can be exchanged. So by tracking different terms in the sum over n, we can get a feeling of following contributions. So here this is just a representative of the full string amplitude. And then upon expansion in n, the first term signals a massless exchange diagram. Okay, I didn't spell it out, but these lines are just gluon lines. And here, from the massless poles, you can see that there's also a massless internal state. That's why it's the same species of lines. But here, this pole here corresponds to a massive state exchange. So here, I'm decomposing the sum into the 0 level and all higher level terms. So from all the terms on the in this curly bracket here, you can immediately read off from the denominators that the internal line refers to a state of mass square. Okay, and if you're carefully working out, and you will find this is mass square equal integer n divided by alpha prime. So in other words, we have just reconstructed the basic property of the string spectrum that I wiped out from here. You can reconstruct this scaling from the poles of the 4-point amplitude. And there's even a little more that we can do here. What kind of states are we exchanging? Let's look at the residue of these poles. So here, these residues involve momentum contractions between here and there. There are some chronicas going on between here and there. So this must mean the vertices here, they contain a couple of derivatives which really allow for tensor contractions. Can a scalar state in the internal line achieve that? No, scalar won't give you these tensor contractions here. So this means we must have objects with indices, and by the number of derivatives, the number of indices grows. So you can already get an idea that the spins grow the same way as the polynomial in polynomial degree s to 3 grows. So schematically, the kind of higher derivative vertices that you can read off from the residues of the poles in S12. This signals that there's higher spin exchange going on. Okay, so this is one interesting way of looking at this intro example, but let me also offer a complementary viewpoint. So we were now looking at the poles for large values of alpha prime, but maybe we want to probe the low energy regime where alpha prime is very small in comparison to the momenta, where the SIJs never get close to these poles. So in short, let's do a Taylor expansion in alpha prime, or low energy expansion instead. So this is what I would call the effective field theory viewpoint on the very same integral. Oops. And in order to have a slick discussion of the low energy regime, let's assume that we have a good math book in our hands. If it's a good math book on special functions, then you might notice that here, this guy in the orange box is nothing but the Euler beta function. And if the math book is really good, then you can also see that it has an alternative representation in terms of gamma functions. And you can furthermore read in that book that there's a nice formula for the Taylor or Laurent expansion of these gamma functions. So that Taylor expansion still starts with 1 over S12. We can't deny in any regime that there's a master-state exchange. But now, instead of tracking the poles in the S12 channel, let's just series expand in both S12 and S23. I mean, all monostane invariants scale with alpha prime, so that alpha prime expansion doesn't bother what the exact labels are. And okay, the math textbook gives you the following leading terms in the expansion of that beta function, and it will be an infinite series. And here we are in the beneficial situation that we can easily spell it out at all orders. So here at 4 points, we are simply lucky that this is a ubiquitous function to textbooks. And at higher points, there might be the need to work a bit harder. You might still get away with hypergeometrics at 5 points, but as far as endpoint alpha prime expansions are concerned, you're probably better be equipped with a good mathematician friend that you can call. All right, and here are some funny numbers. Here are 2 instances of Riemann-Zeta values. The general definition of zeta n is infinite series over integers, 1 to the n to the power k. So I guess you might have come across them in a variety of examples, and also in field theory amplitudes. In many lectures of this week, they will play a prominent role. They are the polylogs evaluated at unit argument, for instance, to connect with David's lecture. And to talk about the physics of these associated SIJs, let me again decompose the amplitude diagrammatically. There's again a master's exchange diagram associated to the pole at the beginning. But now the leftover terms, they correspond to some higher valence vertices. So we draw this internal line because there's a pole. But looking at that term, the pole is gone. So this is something like a contact interaction. This is just a quasi-vertex. And there will be no further pole, no matter how high you go. So what you get is an infinite series in 4-point contact vertices. And for sure, these vertices are decorated with alpha prime to some power and the zeta value. And also, we can do a derivative counting. Maybe it's simplest to do a relative counting. Compare Young-Mills with this first alpha prime correction. there are 4 more derivatives in that correction. Just for reference, the quadratic vertex in Yang-Mills is a to the 4th, with a being the vector potential. Now if I put 4 derivatives on top of a to the 4th, you'll probably get f to the 4th, with f denoting the non-abelian field strength. Yeah? So just by dimension counting and by demanding that this is still a nonlinear negation variant, you can conclude that this must be some interaction with 4 powers of the gluon field strength. And of course this must be a color singlet, so let's better trace it. Okay, by the same token, let's do derivative counting. Let's insist that all the a's are promoted to f's, and you will feel that the next vertex here, with 2 more derivatives relative to here, must have some space-time derivatives. Okay, most naively it's partial, but in the end it should better be nonlinear negation variant, so that's why I'm putting nabla, the covariant derivative. Okay, there's a question?
Yes. What kind of thing are you scattering on? In this scattering, are you scattering what kind of string state? This formula is the same for any...
Oh, okay. Right. So the interpretation, of course, changes depending on where I place this integral. So we are scattering gluons here.
Okay.
And you were probably anticipating that if I were to scatter massive states, I might still find the same kind of integral. So the interpretation here is tailored to seeing the Z4 point inside the 4 gluon amplitude. Okay, yeah, so in summary, when you do Taylor expansion of alpha prime, you can get the fingerprints of effective vertices, higher derivative vertices, and morally they stem from integrating out massive modes. So, since here, in the moment that you Taylor expand, you give up searching for the poles. And this is tantamount to saying you integrate out all these states to whose poles you are blind. Okay, any further question in this intro example? Oh yeah, Justin?
This is a tiny comment, but I think in your Riemann zeta function definition, you switched n and k.
Oh yes, I did. Excellent. Here is the first test of your attention. Thanks a lot. Huh? Okay, remember I was promising you some motivation. Why string amplitudes? And I hope that these introductory remarks are helpful to add a bit more meat to this why string theory discussion. So what I try to convey is that string amplitudes feed in a variety of topics, that you don't need to be a hardliner string theorist to take away some wisdom from them. And let me try to highlight maybe 3 categories of motivation. The first one, I think I already referred to it, is field theory motivation that you can derive, or at least gain intuition about hidden structures in field theory by studying the alpha prime to 0 limit of string amplitudes. So maybe the first incarnation could be in gauge theory amplitudes. There is a notion of color kinematics duality. Not sure, has this been mentioned so far in the lectures? Okay. So this goes under the name DCJ, Bernd Carrasco-Johansson. It's a quite exciting development that, in a nutshell, states the symmetry of gauge theory amplitudes if you trade the color degrees of freedom, the adjoint indices, for the kinematic degrees of freedom, polarizations and momenta. This is already exciting as a symmetry within gauge theory. And this is a property or a symmetry of gauge theory amplitudes that is quite manifest in string amplitudes when presenting them in the right way. But the main motivation to talk about this color kinematics duality in gauge theory is it allows you to stick together two or more, it allows you to stick together two kinematic sides of the gauge theory. So this is what I referred to before as the double copy property of gravity. At the perturbative level and with a sufficient number of quotation marks, you can say you can get your gravity amplitude from squares of suitably chosen gauge theory building blocks. But this only works if the previous line holds. So you need to have the color kinematics duality along the way to make this squaring prescription for gravity amplitudes fly. Okay, and as I was alluding to before, this double copy property of gravity is particularly nice to study by comparing open versus closed strings. And maybe as a third incarnation of the field theory wisdom is, well, there's actually a big web of double copy relations that is not limited to gauge theory and gravity. There are also scalar theories involved in these double copy structures, such as Goldstone bosons, pions, or also Born-Infeld theories. And colorless spin 1 falls into such a double copy paradigm. And to give you a very specific hands-on teaser, this web of double copy relations extends to the tree-level amplitudes of pions. Okay, so my definition of pions here is the kind of colored scalar particle whose Lagrangian goes as follows. So this is also known as a nonlinear sigma model. Here there's the pion field pi, coming with a kinetic term, but also it is dressed by these funny denominators. And if you were to attack that perturbative problem by Feynman rules, you should geometric series expand the denominators. You get a lot of Feynman rules, quadratic vertex, 6-particle vertex, 8-particle vertex. It's a frustrating infinity of Feynman vertices. But this model of pions obeys color kinematics duality, and its tree amplitudes have a nice representation in terms of string ingredients. So let me just drop this as a plane. So here, as implicit in the trace, this is about UN value fields. So there's again a notion of color ordering. And you can obtain such a pion amplitude. You can obtain the result of putting together all these many Feynman vertices. You can assemble that from a single modular space integral. So this is something quite similar to this 4-point open string integral we just looked at. Let's not only do 4 open string punctures, but maybe n of them. And again, whenever you're on this, you're free to fix any 3 of them. You've seen a specific example of that fixing before. Let me write it schematically like inverse volume of SL2 to remind you that you can fix once more. And yeah, as it turns out, you can reach these pion interactions from string theory by integrating something which is called a Park-Taylor factor. Here, a cyclic arrangement of denominators. Just take the difference of all the neighboring punches, neighboring with respect to the color ordering here in the target pion amplitude.
I think you should be at Z1 last one. Instead of 1.
Oh, absolutely. Thank you. Okay, and the juice of the integrand, you've probably seen it before. It's about these factors z raised to some Mandelstam power. And here, in a generic SL2 frame, this is about all the differences. Look at all possible pairs and raise them to the power of the corresponding dimensionless Mandelstam invariant. So one integral fitting all the many diagrams that you can pull out from that pion Lagrangian. But this formula is not only efficient to package all of these diagrams nicely, but also it's something that exposes the color kinematics duality that also applies to the pion. Okay, all of this to exemplify that there are a lot of hidden structures in field theory, not limited to Gaussian interactions and gravity, and that these hidden symmetries involved can be nicely manifested by playing with world sheets. Oops. Okay, so field theory is the first block of motivation. A second block of motivation is that string amplitudes have a fruitful interplay with number theory.
Sorry, this theory of pions.
Yes.
Is it still in 10 dimensions, right?
Oh, actually, this is completely dimension agnostic. As long as you don't use any ground determinant relations between the Mandelstam invariants, you don't even need to commit to the space-time dimensionality with the momenta level. Okay. But okay, it's a bit coward that we are only doing tree level. As soon as it comes to loops, then, yeah, as you know, dimension dependence all over the place. Okay, yeah, so about these number theory aspects, I'm really lucky that there is Claude lecturing on Thursday several times. So I guess many of what falls into this category will be explained by Claude on Thursday. And as you have already seen in a 4-point example, string tree-level amplitudes are a good laboratory for zeta values. And here in the 4-point context, we just see Riemann zeta, but there's a big generalization. In the same way as you can do a lot of different polylogarithms, there is a lot of zeta values that you can generate by evaluating polylogs in unit argument. There's a notion of multiple zeta values, some multi-argument generalization of the Riemann zeta, and these multi-zetas, they naturally show up in the 5-point, 6-point, or n-point function, open and closed strings at tree level. And this number theory direction may be even more exciting at the loop level. By studying the typical integrands for the moduli spaces of Riemann surfaces, you are very, very close to the definition of polylogarithms. I mean, here these d-log z forms, where are they? Unfortunately, they are wiped out. The integrants that you've seen in David's lecture for the polylogs, the same kind of integrants appear automatically in these string theory correlation functions. So you can again look at loop level expressions in string theory, and this is very, very close to the definition of elliptic polylogarithms. So string loop amplitudes are natural playgrounds to see elliptic polylogarithms in action, or to get inspiration of how to organize them. Elliptic polylogs or elliptic multiple zeta values. And these polylogs are already apparent from the open string case, but if you look at closed string set loops, there's another dimension of mathematics coming up, namely so-called modular forms. So this is a fruitful topic of interest in mathematics. And from string theory, by comparing open and closed string loop amplitudes, you get some relations between iterated integrals, like elliptic polylogs, and modular forms, resulting from doing the integrals that a closed string hands you. So these are very interesting connections which from a mathematical point of view are really surprising. But okay, let me take this as a teaser for Claude's lecture. Okay, and finally, let me at least give an idea of some intrinsic string theory motivation to study string amplitudes, maybe the most obvious part, some sort of. You have seen above that the Taylor expansion of string amplitudes gives access to operators in the low energy effective action. And one reason to be interested in these energy effective actions is that they often have a fingerprint of string dualities. Okay, there are various string dualities on the market. Some are strong weak, but others are weak in the coupling. Generically, string dualities will mix different loop orders, but you can study them order by order in alpha prime. So if you have good control over string amplitudes, you can test or exploit string dualities. Oops. And maybe the nicest example of this research program is the type 2b closed superstring theory, one of those which give you the type 2b supergravity. This theory enjoys a self-duality. And this self-duality of type 2b is apparent order by order in alpha prime. You can insist on the realization of that duality in each order separately. And this has been successfully used as a window into the non-perturbative. Like in field theory, there are certain terms in string effective actions that are by definition inaccessible to amplitudes. Whenever a coupling enters through this infamous function e to the minus 1 over g, you will not see it in any Taylor expansion. Such effects exist and are very, very interested in string theory, and by means of string dualities, you might have, in some rare cases, a chance to smell them by using perturbative input plus string dualities. All right. So this concludes the general motivation I wanted to give. So for the rest of the series of lectures, I will follow two sorts of tracks. The first half of the remaining lectures will be of hands-on time. I will walk you through some explicit calculations in conformal field theory. I will drop exercises from time to time. You'll have the chance to get your hands dirty on those. Then in the second half, or maybe in the last third, I will try to give some outlook into what open problems are. I will state a couple of recent research results without attempting to derive them on the blackboard. So that's my rough idea for the rest of this course. And depending on the time and our fitness, I could give some opening equations for the hands-on part. Do you think I could still have 10 or 15 minutes?
You definitely have 10 more minutes. Yes, since you arrived today, the format we decided to have is to plan for 60 minutes of lectures. Oh no, I think I informed you in emails. Yes,
right.
Lectures. Plus 15 minutes of discussion. So maybe it's a good time to stop and ask if there are questions.
Oh, yeah.
Follow on them first, and then if there are none, you can proceed to yes, also write down the fly.
That sounds like a good plan.
Is there a physical interpretation of the first expansion that it is was Z2 that is close to 1, which means Z close that's close to Z3 as far as we fixed stuff. So is there some like underlying interpretation of why you take two vertices to collide basically and have that expansion?
Okay, yeah, you have a very good smell. Yeah, it looks a little bit strange that I strongly favored one channel over the other. I was exposing for you the poles in the S channel, and I didn't have a chance to read off what the poles in the U channel are. And this is one of the really striking properties of string amplitudes. It's referred to as crossing symmetry. I could have done a change of variables, z equal 1 minus x. I could have repeated this game with S channel and T channel exchange. Then I could have exposed all the poles in the U channel, and you would have seen polynomials in S12 as the residues. And it's pretty striking that these two expansions are the same. It's channel duality. There's a very nice account of that in the introductory chapter of Green-Schwarz written 1. At endpoints, you can really decide on your favorite cubic diagram. Expose all the pole channels in a given cubic diagram. And yeah, it's again a super nice property of these dual model integrals that it doesn't matter which cubic diagram you take. Of course, you can ask things in private also later on. In absence of a question right now, I'll take advantage of the extra 10 minutes, hopefully arriving at that point to give you optional homework. Yeah, so the second part is about open bosonic string three-level amplitudes. Now with the details filled in, or at least more details. And here, this will be using some machines of two-dimensional conformal field theory. Just to get a rough overview, how many of you have worked on two-dimensional conformal field theory? Okay, this could be approximately 50% or so. Okay, so you have seen instances of four-dimensional conformal field theory in Gleb's lecture, for instance. And in 2 dimensions, there are some extra yummies that come to the conformal group. For instance, it becomes infinite dimensional. There will be some stages where I use properties of 2-dimensional CFT. If you can't follow them, don't worry. Then just believe it, and I also give you references in where you can study 2-dimensional conformal field theory. So just to already warn you, from time to time, 2-dimensional conformal field theory will appear in the format of divine intervention. Okay, and where does this conformal field theory happen? So a first manifestation is in the Welching age. This will be the starting point of disk amplitude computations. And no matter which genus our Welching has, we can write down a nice 2-dimensional action for it, which also appeared in Gleb's lecture. And I will use a complex coordinate for the world sheet that has 2 real dimensions. And here, this will be a gauge-fixed version of that general sigma model, which you saw in Gleb's lecture, so-called conformal gauge. So let X denote the embedding coordinates for the string, where the piece of string is situated in space-time. And accordingly, there are vector indices denoted by Greek letters. And for most of the time, I will refuse to commit on the space-time dimensionality. Let's just say up to some number of space-time dimensions. And these delts here, importantly, these are world sheet derivatives. So whenever you see a no-name partial, this is a shorthand for d by dz. And here there is an important vertical bar missing. Whenever you see a no-name partial bar, then this is a derivative with respect to the complex conjugate world sheet coordinate. Okay, and this action will, as I explained, be the engine for computing string amplitudes. And we can observe that it enjoys a 2-dimensional conformal invariance. Namely, it is unaffected by a change of coordinates z going to f of z, as long as it's a holomorphic function. So here, of course, these embedding coordinates, they will be fields in the 2-dimensional world sheet that depend on both z and z bar. But here the symmetry is, here, change of coordinates by holomorphic functions f only depending on z. Or likewise, then z bar going to some function g of z bar, anti-holomorphic. To see that this is a symmetry, let's just note that the differential dz transforms in the opposite way as the z derivative. So this is the source of these conformal field theory techniques. But of course, whenever there's a symmetry, we need to worry about it whether it's stable under quantum corrections. So here this would be about quantum corrections from the worldsheet perspective. You may need to worry about conformal anomalies. So without spelling out the intermediate steps, let me state the result. You have a problem with preserving the conformal symmetry unless you make a good choice for the number of space-time dimensions. And here, for the bosonic string model, the correct answer to avoid anomalies is 26. The bosonic string wants to live in 26 dimensions. And by the same token, if you were to do the anomaly bookkeeping for the superstring, then there you find the critical dimension d equal 10. Okay, and a little homework that I planned to pose that concerns correlation functions that you can compute from the worldsheet action. So this will, to give the spoiler, this will be a typical integrand for string amplitudes. And as in any d-dimensional QFT, you can compute correlation functions from the path integral approach. And for instance here, we may want to look at a two-point correlation function of x. To stress it a bit more, x being the embedding coordinate of the string is a field on the worldsheet. And from the worldsheet perspective, it's a scalar. It doesn't have any two-dimensional index. So it's a d vector of scalar fields, vector referring to spacetime. So the Lorentz index is something like an internal symmetry. Okay, so we are computing a correlation function of a scalar field, and the general QFT mantra is that you just insert these fields into a path integral. And we are lucky that the action is quadratic. It's a free field theory with respect to these embedding coordinates. So that integral is Gaussian. And we can compute it exactly. I guess you all have experience with Gaussian integrals. If the integration variable appears quadratically, you integrand next to the Gaussian, then what you have is the inverse of the quadratic operator here. So this Gaussian integral evaluates to the inverse of 1 over alpha prime del bar. Okay, here by saying inverse, I pretend that this is just about our matrix that we need to invert. But here we need the inverse for a differential operator, which is actually its Green's function. So what's the Green's function of this differential operator? In 2 dimensions, the Green's function for this guy is the logarithm. So that's why the 2-point correlation function is this logarithm of the difference, z minus 1. Okay, so this is benefit number 1 of having a quadratic action. And now, if it comes to evaluating higher point correlation functions, then you can grab your QFT toolkit for free field theories and use the Wick theorem. The Wick rules to determine higher point correlation functions. And here's the homework. Convince yourself that by using Wick contractions, you arrive at the following results for higher point correlation functions. Suppose you exponentiate the field x, and then you compute an endpoint correlation function of these exponentiated versions. Let's convince ourselves that what you get is, well, essentially, the process of taking a correlation function exponentiates. Okay, there are a lot of recontractions going on between the different exponentials. Let me encourage you to go through the details yourself. And you just, by doing the combinatorics, arrive at an exponential. But okay, here we can can just insert a two-point correlation function. You can insert the logarithm in the exponent. Well, that's good news. Whenever exponential and logarithms meet, that's news that they are just inverse functions of each other. So that guy becomes particularly simple. Okay, so here I'm already introducing notation of laziness, Zij. So this is the origin of this Koper-Nielsen factor, of this juice of the integrand, as I call it in the 4-point example. But okay, there's one little thing that I forgot. You can say that it's essentially the non-zero modes, which I just treated here. But also there's a zero mode to the field X, which wants us to conserve momentum. These correlators vanish if these momenta, or these charges up here, don't add up to 0. So here, momentum conservation comes from the CFT correlator. If you're not working on the support of momentum conservation, that correlation function, which will later be the integrand for amplitude, vanishes. And to tell you the truth, it's quite cumbersome to have this delta function in each formula. If you forgive me, let me just drop it henceforth. Okay, so homework number 1, work out this correlation function here. And homework number 2, compute a slight generalization of that. Okay, I promise I'll do better with the time management in the next lectures. Second homework is to compute the slightly more fancy correlator. Suppose there are also some dx's in there. And the same plane waves as before. Then the challenge of doing the combinatorics grows a little bit. But I guess it will be plausible that you can do the same kind of big contractions as before. You can still do the big contractions that lead to the plane wave correlator. But now there's some noise coming from these extra fields who are also ready to do big contractions. And by exhausting all the possibilities how to big contract the extra fields, you have one term of Kronecker type. So this term comes from the situation where you big contract these two fellows. And there's a second class of terms when the dx big contracts a plane wave. And this has more alpha primes in it. Whoops. So this will pull down the momentum on the plane waves. And whoops. So this gives rise to these kinds of terms. Yeah, so the exercise is to derive them. Oh yeah, and I was promising you some possibilities to read about conformal field theory. Please don't understand it as a mandatory homework. It's just if next week you find yourself in a relaxed mood, willing to digest some introduction to two-dimensional CFT, and you can, for instance, open up an early archive paper by Ginspark think it's called applied conformal field theory. So this is something you can consult if you want to later on understand the origin of some formula that I'll quote and use in later lectures.
I just want to ask why there are some coincidental points. I think the product of J will start on 3.
Oh, okay, sorry, this is meant to say J is different from 2, but the range is, well, we start at J equal 1. If we just exclude this one. So likewise here. Normal ordering is implicit here in the sense that you shouldn't start contracting fields at Z1 with other fields at Z1.